Hey everyone. This will be a simulation of confidence interval for the population mean. So if you looked at the step-by-step from chapter 14 that talked about sampling distribution, you'll recall that we were working with a data set that had us sampling individuals and the amount of change that they had. Just refresh our memory here. So this was the population. Recall that we had the amount of change located here for each person, right? And the shape of the distribution was roughly normal. What we're going to do now is look at how what a confidence interval is, what it helps us to do, and various ideas associated with those, including the confidence level and the type of distribution that we use when we pick our critical values. So let's take a look. All right, so we'll be working with that last distribution again. So we would want to change this guy here. Instead of the proportions as our statistic, we'll look at the means. Right, and the distribution was a uniform distribution. And we'll look at the method involving the t distribution, the t critical values first. Okay, the lower limit on our values here was 0, and the upper limit is 0.99 cents. Right. Our sample size we want to be above 30, but lower than 10% of the overall population. So let's just be safe. Let's use the one that created the best sampling distribution for us in the sense of the normal shape, and that was the one involving 75, n equal to 75, if you remember. Okay. All right, so what this is going to do for us when I hit the sample button here, with 95% confidence, we would be sure that the population average, which was about 50 cents, is within the sampling distribution, the confidence interval. All right. So let's do that. We're going to take one sample, calculate its confidence interval, and there you have it. So if you notice here, we have this, let's zoom in a little bit. Here is the population average, which is about 50 cents, right in the center of that uniform distribution, 0.495. So roughly the same as what we had before. Now, notice this green bar right here. This is the confidence interval. It's kind of just a visual of it, right? If I click on it, you can see the ends of the confidence interval. So this confidence interval ranges from 0.44 to 0.571, right? And this little black dot in the middle is the average of that sample. The mean of that sample was 0.505. So this confidence interval successfully traps the actual population value. That's 0.495, the population mean, that is. Right? So that's what we're using confidence intervals for, right? This is like an estimate. This range of values estimates the value of the population mean. All right, so let's take another sample and calculate the confidence interval for that sample. Of course, it's going to change because most likely this mean is going to be different. So let's take one more. So there you can see it changed a bit. If I take another one, and it just keeps kind of flip-flopping. All of them are capturing this actual population value. Now note, this population value will most likely be unknown for many populations because populations are just too large to get a census on. But that's why we're using the confidence interval again, right, to estimate this value. So this confidence interval's endpoints would be 0.419 to 0.549. So we would be 95% confident that the true population average amount of change would be between those two numbers. And we can see, we can take a few more. All of these are working for us. Now, you'll notice we get a red one. Now the red one, you can probably guess, fails to capture that value. If we look at the endpoints, it's 0.496 to 0.622. So it does not capture the actual population mean. So again, because we're only 95% confident, we're going to have this kind of 5% chance of being incorrect. And it's possible, based on sampling variation, right? If we get too high, too many high values, or a few extremely high outliers, then we could have this happen, right? So we can see most of the time, 95% of the time, we would get a confidence interval that captures that true value. So let's take a few more at a time, right? Let's take 100 samples of size 75 from this population. So here are all 100 of those. You can see all the green ones are successful at estimating the value of the population parameter of interest here, and that's the population average amount of change. And you see several of these red ones that are outside of that value, right? So they do not capture that number. Now what I'm going to do is just start taking a bunch of samples of size 100, and let's see, we're going to keep our eye on this running total, okay? So the running total of intervals that contain mu, that's the population average, right? So we've taken 110 so far, about 92% of them have trapped that population mean. So if we do that, a bunch more, we can see that as we take more and more and more, that running total starts to approach 95%, right? So we are we've taken about 14,000, so we are right on 95%. That means 95% of those intervals, which is 13,049 out of 14,210, that proportion or that percentage of intervals successfully contain the population mean, which is neat, right? Should correspond to our confidence level. Now let's see what happens if instead we use the z-distribution, right? So let's say we use the z-distribution with our sample standard deviation in order to calculate the confidence interval, right? So instead of using the t-distribution with our 74 degrees of freedom, we just use the standard normal. Let's see what happens. Okay, so reset. And you will see the same kind of thing happen, but so some intervals contain the population mean, and some do not, right? However, in the long run, what happens? We continue to sample here. Notice how this number, the running total, is actually getting a little farther away from 95%. It's actually approaching kind of 94%. We see, right? So this is the reason. This is the reason why we use the t-distribution. It actually provides us with the appropriate level of confidence that we're looking for. If we did not, if we use the z, we would be actually a little bit less confident. So That is why we use the t-distribution rather than the z-distribution when working with means. All right, so that's the gist of our confidence intervals and effects on our confidence level based off of the distribution that we're using.